Hi everyone, my name is Christian Aparicio and I am here to give you a tutorial with the MSC Nastran machine learning web app. Now, for today's demonstration, we're going to go over optimizing a 10 bar truss. So here you can see that at the beginning of this optimization, the weight of this truss is 0.7653 units of mass. And then after this optimization, we get a new weight of about 0.6. Now, why are we using machine learning for this particular problem? Now, with traditional gradient-based optimizers, that method is suitable for linear response optimization. So if you're dealing with linear statics, normal modes, buckling, and so on, the responses you get from Nastran are linear, so you can use a gradient-based optimizer for that. But this problem is a nonlinear response problem. Here you can see that the material is characterized by different relationships, as you can see here in the stress strain curve. So this necessitates the use of other methods that are not gradient-based optimizers in order to optimize this problem. And today here we're using machine learning technology to optimize this 10 bar truss. Now on my YouTube channel, we should probably go there, you can find a full video that goes into the technology that is in this particular video tutorial. So let me go there. So you can search for the engineering lab, Nastran, machine learning. And then here as a presentation called Introduction MSC Nastran Machine Learning. So if you want more of a theoretical or an explanation of what's happening in the background during machine learning, I recommend you watch this video. Now going back to today's tutorial. So just to quickly recap, this problem features nonlinear responses, so a gradient-based optimizer is not ideal. As an alternative, we're using machine learning to improve the performance of the structure. Now let's go over the optimization problem statement. This is the first thing you should have with any optimization problem. You should clearly define what your variables are. Here, the variables are going to be the cross-sectional areas for each member of the truss. We're going to allow the variables or the areas vary between 78.5 and 2,826. Our objective for this is to minimize the weight response, and our constraints are going to be constraints on the axial stresses for each member. And then for the displacements, we're going to constrain the X and Y components of translation for all the free nodes. The two nodes at the fixed end are going to be, well, we don't need to apply constraints there. Let's see, let's go on to the next one. So, quick reminder, just in case you have any optimization questions related to MSC Nastran, they can be MSC Nastran Solution 200, or they can be machine learning. Please feel free to contact me at this email address. I have worked with multiple students, multiple professional engineers over the last few years, so I've accumulated a lot of experience in this area of optimization. So again, you're welcome to contact me at this email address if you have an optimization related question and related to finite element analysis. Now, let's start with the tutorial. Before getting started, typically for myself, I like to start with the clean downloads directory. Since we're dealing with the web browser, this downloads directory is typically where the browser downloads all your data. So let's have it clean for this tutorial. Let's go ahead and go to the user's guide. And when you go to the user's guide, there's going to be a section called tutorials, and here we'll navigate to the machine learning tutorials. And what we need first are the starting files. I've already taken time to construct this PDF file. So that would be this file that's in here. it's already got the problem or the analysis model. Every node, every element, and so on is defined. So that's already been done. Once I have this PDF file, I need to run Nastran so I can generate the H5 file. The H5 file is going to contain all of the responses I need, the weight, the stress, and the constraint responses. So once you have the BDF or the DAT file, and once you have the H5 file, we can now come back to the web app, click on machine learning, which will open the machine learning web app. And now I can start the process of configuring my problem statement in this web app. So if I click select files, I select the DAT file. And here are all the bulk data entries I could configure to be parameters. Here for prod1, I'm going to select the cross-sectional area field. And then I'll repeat the process for prod1 through 10. And then for the bounds, let me just go back to the problem statement and look at the bounds we're using. Here we're using 78.5 and 2,826. 78.5, and let's just go ahead and copy and paste for the other ones. Now, after I'm done configuring these bounds, I have the option of configuring the comments. Often when you're looking at the results, you're going to be seeing the change of x1, x2, and x3, but later on you're going to be asking, what does x1 correspond to? What does x2 correspond to? This is where you can specify what the variable is in the comment section. By default, you have this description here, but you can customize it if you want. Here I could say cross-section of element, cross-section area of element 1. You could customize the comments here. So later on, when you're looking at the results, you have this description to help you identify the variable. Now, once I'm done selecting the parameters, I need to specify what's called the training data. Here, I need to configure different combinations of the parameters, different combinations of the FE model. Later on, I'm going to run Nastran at each different combination. I'm going to generate the output or the responses, and all of this is going to be used to train a surrogate model that the machine learning web app uses to improve the design. I'll go into that later on, or more into this later on. So here for the design, I'm going to use the land hypercube design. Here it says reproducible. What this means is that anytime that I select this option, it's going to be the same design. The true land hypercube design is different each time you generate it. But here it's using a static design, if you will. It's reproducible. So if I come back tomorrow and I select this option, it's going to give me the same design. But if I just select the true land hypercube option here, you can see that anytime I modify this design, it will be slightly different again and again. So here, let's go back to the reproducible design. And here I'm going to use 5 runs per parameter. Since I have 10 parameters and I'm using 5 runs per parameter, I need a total of 50 runs to generate my training data. So you can see here that I have samples 1 through 10, and then if I go through each page, I have eventually 50 samples. So Nastran is going to be used to run all of these different configurations. Sample 1 with these cross-sectional areas, sample 2, 3, 4, and so on and so on. Now let's go over to the responses. For this, let's go ahead and select the H5 file and upload it to the web app. The first response I want to select is the weight response. So here on the left, I picked this grid weight data set. Here you can select anything that's a single value, and here I have 0.263, which is the weight or the mass. And then here on the right, I have the weight response. Next, let's go ahead and select our axial stress results or responses. So here on the left side, I'll click dataset stress rod. Here, if you look at the axial stress column, these are the axial stresses for each member of the 10 bar truss. So I'm just going to select all of these responses for now. Now the displacements, like before, I'll select the displacement data set. And then I want to constrain the X component of the grid. So let's go ahead and select the X component. And I want to select or constrain the Y component of the grid. So let's go ahead and select these responses. So everything you click on here is added to this right section of this responses section, if you will. Now here I have R1, which corresponds to weight, R2 through, well here what we can do is shift this over. Here on the top right hand corner are two arrows. You can use this to increase the width of the left or the right section. So this first response is the weight, so I want to minimize the weight here. This next response is the axial stress, and here I want to constrain it to negative 220 and 200. So the stress should be between negative 220 and positive 220. And let me go back to the problem statement just to make sure I'm typing the numbers in correctly. And then here for the displacement, it is to range between negative 100 and positive 100. And now let's just go ahead and copy and paste the response or the bounds for the constraints. Okay, let's go ahead and finish this. Now, you may notice that here when we are selecting responses, we use the H5 file. I know there are other applications that use the F06 file, but here the preferred method that we use is the H5 file. So now let's go ahead and make sure I've typed in all these values correctly. Negative 100, positive 100 for the displacement constraints, and then negative 220, positive 220 for the how do I say, for the axial stress constraints. So 220 here. Okay, let's go ahead and look at all this and make sure it's correct. Okay, looks good. Let's go ahead and shift these columns back to where they were. Now, before downloading, let's go to the settings section and let's switch the option to machine learning. You can see that there are other options like a local optimization. This is powered by a gradient-based optimizer. You have sensitivity analysis, also powered by a gradient-based optimizer. And then there's a machine learning option that's powered by Bayesian optimization. And here, just in case you're wondering how it's written, we're powering machine learning through what's called Bayesian optimization. So now, let's go ahead and configure a few things here. We want to run machine learning for an extra 30 runs as an example. So I'll type in 30 here. So what will happen first is Nastran will run for 50 samples. The surrogate models, if you will, for each weight, displacement, and stress constraint will be constructed first. After these 50 runs, that's when the machine learning process starts. The machine learning process will run for an additional 30 runs. So in total, we will run Nastran 80 times, or 50 plus 30. Now, for the acquisition function, the YouTube video I mentioned earlier goes over the machine learning technology. In that presentation, I go over acquisition functions. There are two acquisition functions available. The first one is called the expected improvement acquisition function. The second acquisition function available is the probability of improvement criterion. Now, when do you use both? If you're dealing with 1 through 5% parameters, you can use what's called the expected improvement criterion. But once you get up to higher dimension problems, maybe you're dealing with 8, 10, 15, or 20 parameters, the design space is very large. You would have to explore a lot before you find an improvement in your design. So an alternative to the expected improvement criterion is to use what's called the probability of improvement criterion that I have here. So this problem is using 10 parameters. When I've tested this with expected improvement, it works, but it takes a long time to search the big design space. An alternative is just to use probability of improvement, which I've selected here. Now, let me do one last check with all of my parameters. So here I have x1 through x10, the bounds. I'm running 50 samples to generate my training data. I've selected the weight, the stresses, the displacements, the settings. Okay, everything looks good. Let's go to the download section and download the zip file for this. So this zip file is going to contain all of the BDF files that I need to perform the machine learning optimization. So let's go ahead and extract the contents to my desktop. And let's go ahead and start the process by clicking the desktop app shortcut. Now, in a moment, this desktop application is going to open the status page and the machine learning results page that shows you the improvement in real time. Before I go into the results, I should mention one thing for Windows 10 users. Windows 10 spacebar, CMD stuck. I noticed that on Windows 10, there is what looks like an issue. On Windows 10, if you click the window of the command prompt, it will stop what's running in the command prompt. When you click in the command prompt, the command prompt says select. This pauses the entire process. You have to press spacebar to, continue the process. So I'm just letting the Windows 10 users know this because this was it kind of prevented me from completing this example, and I wanted to let you know that this is the reason why the command prompt is pausing. You click the black area, it pauses the command prompt. To unpause, you have to press the space bar. And of course, if you really want to just disable this, you would modify the settings and disable quick edit mode. Now, going back to the tutorial, what is happening now? Let's go back to the tutorial PowerPoint and let me navigate to the slide where I discuss this. So remember that the first 50 runs, so that would be from here to here, this is going to be used to construct what's called the training data. And here I'll just write TD. This training data is going to be used to generate the surrogate model. Now, the surrogate model is going to be used to predict the output of Nastran without actually running Nastran. Once you have this new surrogate model, you use the surrogate model to build the acquisition functions. So I think a better example would be to refer back to my machine learning presentation here. So we're in this phase. We're just running Nastran multiple times at different combinations of the parameters. And this is going to generate my training data. Eventually, I use the training data to fit my surrogate model. And in our conversation, we are using what's called Gaussian process regression to create the surrogate model. We use the surrogate model to build our acquisition functions. The acquisition functions helps us select a candidate point that might be a better design. Once we have this candidate point denoted by X, we plug it into Nastran, where Nastran could be seen as a black box function. We run Nastran again. After that, we get new output, and then we update the model again with this new output. And then we just repeat the process again and again. We fit a surrogate model. We generate our acquisition functions. The acquisition functions yield a candidate point. We run Nastran. We update the model, and we just go in this loop again and again. So that's what's happening at the moment with Nastran. So what will happen after 50 runs, this is where the machine learning process starts. So after this, you can see that the machine learning process starts to find better candidate points again and again. Eventually, you get to a point where the longer the machine learning process takes, the less improvement is seen in the optimization. You can see that towards the end of this, you don't really reduce the objective anymore. Now, this plot I'm showing you is referred to as the best valid value plot. You might be asking, what is this best valid value plot? And I can actually show you with these bar charts. So remember, the first 50 runs are being used to generate the training data for the initial surrogate model. Here you can see that some of these different configurations, these different samples are feasible. They're green, indicating they're feasible. They satisfy all the constraints. The gray bars indicate that this design or sample 26 does not satisfy all the constraints. So we take all the different configurations, all the different samples, and we find the best minimum so far. You can see that sample 34 is yielding the best minimum so far, and here the objective is 0.76. If we go back here, you can see that it's reporting 0.676. So here, this is the best observed objective value so far in the process. Here we're at the end of sample 50. So we've generated the training data with 50 runs. This is where the machine learning process starts. You can see that in the next run, the machine learning algorithm is going to use the acquisition function to pick a candidate point. Now, it's going to either find a better or worse design. You can see that for run 51, it generated a new candidate point, but the design is infeasible. That means that this design does not satisfy the constraints. So when it keeps doing this, eventually it will find a better design. You can see that after sample 52, it has found a better design with a better objective that's feasible and satisfies the constraints. And the machine learning process will continue on. Here you can see that the BVV, or the best value has been improved. Back in the settings section of the web app, we configured this to be 30 runs. So here you can imagine that after 50, it's going to go for 1, 2, 3, 30 additional runs. So at the very end, it should end at 80 runs. So I think at this point, let me go ahead and pause the video here and just wait until the 80 runs are over with. Now, we're almost done with this optimization. There's one thing I wanted to bring up here. So here's so far the best design found so far by the machine learning algorithm is sample 64. That would be this one. If you use the bar chart here or the table, we navigate to sample 64. We see what the new objective is, which is a 0.533. And our normalized constraint is about negative 0.2. Now, negative 0.2, that is how do I say, if the here I'll use this definition, if the design was perfectly on the, or rather, eventually you're limited by your constraints. So for example, your stress constraint in this tutorial is between negative 220 and positive 220. Your optimized model will have a response that's right on the bound. So for example, you could end up with a stress that's right at the bound of 220. But here we're being told that the max normalized constraint is negative 0.2, negative 0.2 rather. If the response was right on the bound, the max normalized constraint would be 0. But here what I'm basically trying to say is that there's still room to improve this design. You could use machine learning to further improve the design. You could get this value of negative 0.2 to maybe positive, or rather to 0, but it would take a very long time. What you can do instead is you can take this best design so far, you can go back to the machine learning web app, and you can just use local optimization. You can start from that best point found so far and leave it up to the gradient based optimizer to polish or finalize or improve the best design found so far. After the optimization is complete, you'll get a list of H5 files. You can just skip this part. Usually what happens at this point, you get an option to open what's called the HDF5 Explorer. So if you wanted to make plots, you could use this tool, click continue, and it would open the H5 file. But here we're not interested in that, so we'll just click skip. And now here we'll see that the best design found so far was here at sample 64. Let's see, what one last thing I wanted to do. Now, when you perform this optimization example, you will get a slightly different path here. And that's because of the way the algorithm inside of works. Since you're searching a very large design space, the algorithm internally is randomly selecting points to facilitate the exploration. Part of the search involves the acquisition functions. Another part of the search involves selecting different points of the design space to find the best optimum. Now, this randomization, if you will be different from person to person and time. So if I were to repeat this tutorial again, this machine learning process, I might get a different machine learning path, if you will. But at the very end, I should get an objective close to this 0.533. After you're done with your machine learning task, you can then switch over to local optimization and further improve the best design found so far. Now, that was the end of this tutorial. The one thing I wanted to leave you off with is my contact information. Now, as always, if you have any questions or comments regarding optimization with Nastran, you are more than welcome to contact me at this email address. If you're dealing with MSC Nastran Solution 200, if you're dealing with machine learning, please feel free to reach out to me with your questions. If you're dealing with a different finite element analysis solver, you're also welcome to contact me. With that, I'll go ahead and stop the video here, and thank you so much for watching. Now, there was one thing I forgot to mention. Suppose that you close everything, and then you come back tomorrow morning and you want to continue the process. How do you bring all your files back? How do you restore your files in the machine learning web app? reload the page, so it's a new page. There shouldn't be any new samples or parameters or anything like that. Go ahead and navigate or click select files, go to the Nastran working directory and just select all of the BDF files and the app configuration file and click open. When you select all of those files, the web app will bring in all of this information and it will restore all of your parameters, your samples, responses, and everything else. So if you wanted to reconfigure something, you can do that. Maybe you want to delete some constraints. Maybe you wanted to add new responses. You can also do that as I'm showing you here. You would re-upload the H5 file, and then here you could reconfigure your, your responses. So that was the last thing I wanted to leave you off with. Thank you so much for watching.